Hey there, everybody. Welcome back. We're in Calculus 3. This is Anton's 11th edition book where we're doing 15.7 Divergence Theorem. This is College of the Sequoia. It's fall 2022. This is our last video for 15.7, and it's on the continuity equation. Huge equation in physics. And believe it or not, a lot of how we make things work. Airplanes fly, things that things that go underwater, things that move through fluids. We need to and how fluids work anywhere. So we're going back to that fluid flux. F is the density times the velocity. And we're going to look at a sphere of radius alpha centered at a point P naught. So we got this really small circle or sphere. The center is P naught. The divergence of F from that point right there shouldn't be much different than another point within that sphere. So any other point in that sphere for a small radius should have the same divergence. There's no reason to think the flow or density is going to change a lot, or the surface is going to change a lot, moving away from that surface a little bit, especially if we do as alpha goes to 0. Then the divergence of F at P naught, which should be similar, it should be the same thing as the divergence of F at P. So we're exploring this right now. This is our equation for divergence, and we're going to evaluate it at P naught. But for small things, it equals the divergence of this is a value. Divergence of F at P naught is a value. It's not a vector. We can factor it out. We're doing a small sphere, so the triple integral dV just turns into volume of the sphere multiplied by the divergence. So we could say the divergence, we divide volume over, and we say the divergence of F at P naught is the the flux through the surface divided by the volume that it encloses. Okay, and I did divided by the volume as 1 over the volume up front. That's what this is. The divergence at the point is the surface integral, or the flux of the surface integral divided by the volume. Okay, and that's as alpha goes to 0, so at any point inside there, it doesn't matter. So what is the divergence of F at P naught? It's the net rate of outward flux per unit volume at P naught. That's why we call it divergence. It's how much is diverging away from the point. If that is greater than 0, there's outward flow, and there must exist a source inside that small sphere or inside our surface. If the divergence is less than 0, then more stuff is flowing in than outward. We have a sink inside. Something's making stuff disappear. And if the divergence sphere is equal to 0, there's no flux. That doesn't mean there's not stuff going in and not stuff going out. It's just the amount going in is the same as the amount going out. We had F is rho of the density times the velocity. There's flow, but the divergence isn't changing. The velocity isn't changing. We said steady state. So the velocity isn't changing. The flow isn't changing. That means the density must not be changing either. So the density is remaining constant. This is used a lot in hydrodynamics. It's called the continuity equation. So the continuity equation for incompressible fluids is rho v. Working with rho v. Here's the Navier-Stokes equations. You can see it here. V is the velocity UVW. The continuity equation is the change in density over time, added to the change in density at each different point of the velocity, has to equal 0. So this shows up in the Navier-Stokes equations. This is the unsteady state, which is why we make sure we include the time component. So these are the three-dimensional Navier-Stokes equations. There's a lot going on. See, we've got rho v in a lot of places. U, v, and w's are components of velocity. This shows up in a lot of places, okay, for momentum and stuff like that. We have our energy equation. All of these have to be solved simultaneously. If you like astrophysics, if this is what you're interested in, astrophysics kicks it up a notch and adds magnetism. If you want to know more, give me a holler. It was my graduate research. That's it for the divergence theorem. Just remember the divergence theorem is, bring it back up. F dot n ds, the flux over a surface, is the same as the divergence over the volume. Okay, peace.